Hello, I'm Hardy Flickinger with LJ Star Incorporated. Today, our tutorial is how to select and maintain sight glasses for chemical and pharmaceutical applications. If improperly specified, installed, or maintained, sight glasses can be the weakest link in a processing system because they can limit observation capabilities, require frequent maintenance or replacement, or make it difficult to illuminate the vessel in which they're installed. Additionally, sight glasses can fail, endangering workers and causing extensive destruction and system downtime. When glass fails under pressure, it is sudden and catastrophic. Glass can fracture at 5 miles per second. Here we have a comparison of the two most commonly used sight glass materials, borosilicate glass and soda lime glass. I'll talk about each one separately and their individual benefits. Before the development of borosilicate glass, almost all sight glasses were made of soda lime glass, a common, relatively inexpensive glass which is used in bottles, light bulbs, and window panes. This glass is typically made from silica, soda, lime, magnesia, and alumina. Soda lime glass is widely used for low pressure, low temperature, and non-caustic sight glass applications. Borosilicate glass, which was originally developed by Corning under the brand name Pyrex, offers high strength, the ability to withstand temperatures, high corrosion and chemical resistance, and high thermal shock resistance. In addition to sight glasses, borosilicate glass is used in cookware, lab equipment, and glass pipe. It's made from silica, boric oxide, and alumina. The boric oxide enhances its stability and helps to bind the rest of the elements together to prevent leaching. This formula is used to evaluate a material's thermal shock resistance. Borosilicate glass offers much better thermal shock resistance than soda lime glass. Thermal shock is directly related to the thermal conductivity. The glass material selected, the unsupported diameter, and the glass thickness all play a role in determining the pressure capabilities of a sight glass assembly. This graph illustrates how borosilicate and soda lime glass perform at various working pressures and temperatures. Note the higher working pressure capabilities as the temperature increases for borosilicate glass compared to soda lime. Borosilicate glass offers much higher chemical resistance than soda lime glass, which is important to prevent the breakdown byproducts of the glass from being introduced into the manufacturing product. Glass is not chemically inert, and even water can degrade its surface over time. Chemical degradation from caustic or acidic substances or pitting from mild abrasion can dangerously weaken glass, obscure its transparency, and create crevices where bacteria can hide or leach into the processed media. Annealed glass has been slowly cooled to prevent buildup of internal stresses, so it can be cut and further processed. After annealing, the glass can be further strengthened by tempering. There are two methods to temper glass. In the first one, chemical strengthening, a chemical solution is applied to boost the mechanical resistance of the glass. In the second method, thermal tempering, annealed glass is heated to approximately 680 degrees centigrade, almost its softening point. The glass is then quenched or cooled with a steady high-pressure flow of compressed air. This process quickly cools the surface, which goes into compression while the core is allowed to cool more slowly, which then goes into tension. This process makes heat-tempered glass 3 to 5 times as strong as annealed glass. Rapidly cooled, fully tempered glass, when fractured, releases the tensile energy stored in the core and breaks into many fragments, much like automotive glass and glass basketball backboards. If, instead of cooling the glass rapidly, it is allowed to cool slowly, it becomes only twice as strong as annealed glass. When fractured, these broken glass fragments are linear and will normally remain in the frame. Thermally tempered glass is often used in conventional sight glasses. In addition to tempering, glass can also be strengthened by placing it in mechanical compression. Fused glass sight glass windows, like Metaglass, offer high pressure capabilities and high safety margins. The strongest type of fused glass sight glass windows are made from duplex stainless steel and borosilicate glass. This combination creates the highest compression. During heating, the glass is melted within the metal ring as the ring expands. The glass and the metal ring fuse together. When the unit cools, the glass hardens before the metal ring shrinks back to its original size. This process places the metal ring in tension and the glass in uniform radial compression. Glass can tolerate very high levels of compression. Radial compression improves the performance of the glass because it offsets the effects of tensile strength. Under this strong compressive force, the glass, in effect, becomes elastic. The metal ring enhances failure resistance because mounting and sealing pressures are applied to it rather than the glass. Even when bending forces extend beyond the metal ring into the glass remains elastic and able to tolerate bending. Fused glass sight glasses won't shatter even under extreme bending force. They can fail safely because they retain elasticity. Any number of factors can contribute to a sight glass failure like the one you see here. A sight glass failure can be attributed to improper assembly design, such as flanges that are too thin, too few bolts, a cushion gasket that is too soft or too thick, or inadequate glass thickness. There's also the potential for improper installation, such as over-tightening, uneven torquing, or debris trapped between the vessel and the sight glass. Manufacturing defects, such as flanges or glass that don't have flat and parallel surfaces, can lead to failures. Incorrect use and mishandling that introduces microscopic surface defects can also require premature replacement. Reusing commercial conventional glass discs and gaskets during maintenance and inspection can also create an unsafe situation. Both glass discs and gaskets should be replaced every time. Unknown variables during processing, such as thermal shock, shadowing, and overpressurization, can also cause early failures. Glass can simply degrade over time due to corrosive chemicals or erosion from friction from the process media. Finally, for clamp-on sight glasses, which are widely used in the pharmaceutical and food production industries because they allow all components to be disassembled for easy cleaning or reconfiguration, the wrong clamp can lead to big problems. Always choose clamps designed to withstand the level of pressure the sight glass will experience. This formula will allow us to calculate how thick your sight glass window should be based on the pressure differential it will encounter. Generally, the thicker the glass, the higher the pressure it can withstand, and the lower the resultant overall stress. These are critical standards you'll see on sight glass data sheets. DIN is a German standard. ASME is the American Society of Mechanical Engineers standard, and BPE stands for Bioprocess Engineering. We'll go more in depth on these standards in the next few slides. Here's an overview of the technical specifications associated with the DIN 7080 spec from 2005. With this specification, there's an allowable continuous working temperature of less than 536 degrees Fahrenheit, and the maximum allowable working temperature is less than 572 degrees Fahrenheit. Keep in mind that when working temperature is greater than 536 degrees, the glass must be protected with mica film and replaced after 300 hours. The thermal shock resistance, ISO 718, is 446 degrees Fahrenheit. Hydrolytic resistance, ISO 719, is class HGB1. Silica glass having a very high hydrolytic resistance due to its composition contains significant amounts of boric oxide. This test keeps classified glass resistance to chemical attack by heating the glass in contact with water. The acid resistance, according to ISO 1776, and the alkaline resistance, according to ISO 695, is shown in the slide, along with the linear thermal coefficient of expansion. The 2005 standard applies to pressure-resistant circular panes of glass made of thermally toughened borosilicate glass, which are designed to withstand a continuous one-side fluid pressure at temperature up to 536 degrees. The standard does not apply restrictions to the use of borosilicate glass panes below ambient temperatures. To meet the DIN 7080 standard, the glass must meet the hydrolytic resistance requirements, which means it must have the appropriate proportion of boric oxide. This should measure between 8% and 13%. Boron trioxide performs a primary function as a binder that holds the silica sand, soda, and ground lime. This is known as the recipe for borosilicate glass throughout the chemical and pharmaceutical processing industries. Borosilicate glass is the least reactive glass for sight glasses for observing unbuffered products, caustic chemicals, SIP, CIP processes, tank cleaning validations, and more. Metaglass is the best known of the Type 1 sight glass brand names. Take care when selecting glass for applications where the pH is very low or very high, because even Type 1 glass can be subject to attack under certain conditions. Although Type 1 borosilicate glass has the least pH shift of any glass, there still may be some sensitivity with certain packaged products. Surface treatment is not usually required. However, such treatments can further enhance the desirable characteristics of an already superior material. USP Type 2 dealkalized soda lime glass has higher levels of sodium hydroxide and calcium oxide than Type 1, and is also less resistant to leaching than Type 1, but more resistant than Type 3. It can be used for products that remain below pH 7 for their shelf lives. The most common applications for this glass are for storing containers for alcoholic spirits. Dealkalized treats the inside surface, so there is less extractable alkali. USP Type 3 soda lime glass is generally not used in sight glasses, but is acceptable in packaging some dry powders that are subsequently dissolved to make solutions or buffers. Type 3 glass is also suitable for packaging liquid formulations that prove to be insensitive to alkali, but shouldn't be used for products that are to be autoclaved. Trade names include Wheaton 800, 900, and Scott B270 Super White. The introduction of B270 Super White made it much more difficult to identify soda lime glass. Prior to this, soda lime was easily identified by its green hue. The super white formulation made it much easier for cheaper knockoff brands to be passed off as the more superior borosilicate material. USP type NP soda lime glass is general purpose glass used only for non-injectable drugs. These applications where chemical durability and thermal shock are not factors, but has the greatest risk of etching and leaching in process environments. Soda lime glass does not include the measurable levels of boric oxide needed to maintain stable glass, which can lead to the leaching and extraction of core elements into the process. It's the least capable of effectively dealing with CIP and SIP requirements in pharmaceutical applications. Trade names for the type of glass are Wheaton 810, 910, and Boro Plus. Here's a good example of a bad sight glass choice. In this example, an independent inspector for an injectable drug maker mistakenly recommended installing more powerful lights for inspecting vessels for cleanliness. In fact, the light ports were made of soda lime glass and had etched so badly that the light could not shine through them. The light port shown here also shed a glass shard into the process vessel, which is another big problem from a safety and product contamination standpoint. It should also be noted that these parts are often light ports, which can go unnoticed for long periods of time in between inspections, as long as the light is operating normally. Make sure you don't spend all your time looking through the window. Also spend some time looking at them. We have several sight glass maintenance tips to share based on our many years of industry experience. For example, once a conventional sight glass has been removed from its mounting for any reason, discard the glass and gaskets and replace them with new glass and gaskets. The exception to this rule is Metaglass. These safety windows, which may be installed with new gaskets following the instructions provided for this procedure. Other tips include making sure you keep glass clean using commercial glass cleaners, never using wire brushes, metal scrapers, or harsh abrasives, and not attempting to clean glass while equipment is in operation. To examine the glass for scratches, shine a bright concentrated light source at an angle of about 45 degrees. Anything that has a glint should be inspected closely and could be a cause for replacement, including scratches that catch the fingernail or any star or crescent-shaped marks that glisten. Sight glasses that appear cloudy or roughened after cleaning should be replaced. Finally, always inspect sight glass frames or flanges for corrosion or buildup. Regarding installation, never use glass that is scratched, chipped, or otherwise physically damaged. Glass seating surfaces must be flat within 5/1000ths of a smooth finish. Flanges must be rigid. Don't allow the glass to contact metal when assembling. Gaskets must be new, clean, and smooth. Only use gaskets the same diameter and fit them consequently. Remember to never tighten bolts on a sight glass while equipment is in operation or when the sight glass is hot. Follow a regular tightening sequence to ensure even loading of glass. Allow a maximum difference of 1.5 foot-pounds between bolts during tightening, and tighten only enough to produce a positive seal against the process pressure. Bolts may need to be tightened after initial cycling of the vessel.